Buffer solutions resist changes in pH. And so let's think about a solution of a weak acid and its conjugate base. So here we have HA, which is our generic weak acid, and so the conjugate base would be A-. And a buffer solution needs to have substantial amounts of both present, and that's what I'm trying to represent over here. So we have a beaker, right, that has, in this case, equal amounts of HA and A-. And to our buffer solution, we're going to add some strong acid, so a source of protons. So I'm going to draw a proton in here, so H+. I could have written H3O+, because H+ and H2O give you H3O+. I'm just writing H+ to make it a little bit easier to think about. So if you're increasing the concentration of H+ ions, or you're increasing the concentration of hydronium ions in solution, you would think that would decrease the pH dramatically. And that would happen if you didn't have something to react with the protons in solution. But we do in our buffer solution, right? We have A-, we have our base. The base is going to pick up this proton, and H+ and A- are going to form HA. So we're going to make more of our weak acid here. So let's see, we started out with some weak acids. Let me go ahead and draw that in here. So some HA. And then we're going to make more because H+ and A- give us HA. So we're making more of our weak acid here. What about A-? All right, well, we're going to use one of these up to make HA, right? So now we have only two of these left. So we're decreasing the concentration of A-. But what we've done is we've effectively removed protons from solution, and that's how a buffer is able to resist a change in pH if you add acid. What about if you add base? So next, let's think about our buffer solution. And this time we're going to add a strong base. So we're going to increase the concentration of hydroxide ions in solution. So if we increase the concentration of hydroxide ions in solution, you would think that would increase the pH, right? And it would, except for the fact that we have an acid that can react with our base, right? So we have some weak acid present here. And the hydroxide ion is going to pick up a proton from HA, right? So we have H+ here. So OH- and H+ give us H2O. So we're going to make water here. Right, so we're going to lose some of our weak acid. So we started with 3, and now we have only 2 left here. And if OH-, if hydroxide takes a proton away from HA, then we're left with A-. So we're going to increase the amount of A- that we have, right, in solution. So let me go ahead and draw that in here. So once again, we've effectively buffered against a change in pH because the hydroxide ions that we added, right, were reacted with the acid that was present. So we've effectively removed hydroxide ions from solution. All right, so that's the idea of a buffer solution. Let's see if we can derive an equation that will allow us to do some calculations. And so next, let's look at what we have down here. Right, so we know that we have in a buffer, we have substantial amounts of HA and A- present, and so we have this reaction at equilibrium. So for our equilibrium expression, right, concentration of products over concentration of reactants. So here we have our concentration of products over our concentration of reactants, once again leaving water out. Let's take the negative log of both sides of this. So we're going to take the negative log of Ka, so that would be negative log of Ka here, and the negative log of all of this, which would be equal to the negative log of all of that. And I'm going to write it a little bit differently. I'm going to put the concentration of hydronium ions out front here, and then have concentration of A- over concentration of HA. All right, I wrote it like this because it makes it a little bit easier to see a property of a logarithm. Let me just go ahead and write down the property that I'm referring to. If you have log of A times B, that's the same thing as log of A plus log of B. And here we have the negative log. So the negative log of AB is equal to the negative log of A plus the negative log of B. So I'm just going to write minus the log of B here. And in this case, right, concentration of H3O plus, that would be A. Right, so this would be A, and then this over here would be B. All right, so let's think about what that would give us now. So let's get some more space, and let's think about our log property. So on the left side, we have negative log of Ka, and the right side, we would have negative log of A, so that would be negative log of concentration of H3O plus, right, minus the log of B here. So that would be minus the log, and B was this right here, minus the log of A minus over HA. All right, so we can keep going here because we know the negative log of Ka, right, the negative log of Ka is equal to the pKa. So this is equal to the pKa. And then over here we have the negative log of the concentration of hydronium ions. That's equal to the pH, right? So negative log of concentration of H3O plus is equal to the pH. And then we have minus log of the concentration of A minus over the concentration of HA. And so we can rewrite this in for our final equation. So we're just going to rewrite this, solve for pH. pH is equal to pKa plus the log of A minus over the concentration of HA here. And this is called the Henderson-Hasselbalch equation. So right here is the Henderson-Hasselbalch equation. It's very useful when you're doing buffer calculations. All right, we'll look at examples of this in the next video.